Natural language is about text, alphabets, words, sentences, numbers, special characters, emoticons. In a nutshell, every way we express our thoughts. Now, I cordially invite our next speaker, Ms. Nabanita Roy, to conduct the session, Word Embedding for Text Classification. Ms. Roy, who is from Ireland, is a data scientist at ACI Worldwide, a blogger at Medium, and an education co-lead at Women in AI Ireland. Hello, Ms. Roy. Thank you for joining us today. Over to you.
Hello, everyone. Thanks for the lovely introduction. um, let me share my screen and then start. Just a second. All right. Thank you, everybody, for joining this talk. I will be presenting bits and pieces of word embeddings for text classification. A little bit about myself. My name is Nabanita Roy, and I work as a data scientist at ACI Worldwide. I also work with Women in AI Ireland to promote to promote AI amongst women, and especially look after the education track. I'm currently based in Ireland, but I'm actually originally closer to Sri Lanka. I'm an Indian. I'm from Calcutta, so yeah, I was really looking forward to this talk. Um, the agenda for today we have is um, so we will be discussing what is machine learning and how is it applied in natural languages. What is the need for us to transform texts to numbers? We will also look a little bit into vector space model because that is a core concept here when you're representing numbers, texts in numbers. Also, briefly, we will look into the traditional text representation techniques, the caveats they have, and then how word embeddings address those caveats. And a specific school of algorithms, Word2Vec, for generating word embeddings. And then two methods of these algorithms that we can use to create word embeddings as well. And then at the end, we will have a demo in Python using GenSim. So I have listed a few prerequisites here for the demo. So just in case you don't have these installed already, and if you want to follow along with this demo, you can download Pandas NLTK GenSim, TensorFlow Keras, and if you're not using Jupyter Notebook, then you could go to Colab as well and try to copy the code that I'm working on here. You can also go to this GitHub link to get the talk resources. Let me share this in the chat. So this is the link that I have. You can download the materials that I'm using right now from this repository. And GenSim does take a while to get installed. So if you can start downloading it now while listening to the talk, it would be great. And apart from that, I've used Plotly. That's optional. If you can skip that, and you can do it with Matplotlib as well. And I've also uploaded an HTML version in the same repository of the notebook, so that if you don't want to execute the cells, you can just follow through you on that HTML page of a version of that notebook. All right, so we start here with our first question. Very basic, what is machine learning? So machine learning is a branch of artificial intelligence and computer science that focuses on the usage of algorithms on data to imitate the way that humans learn. Now, the thing that we call here data, when we think about data, we generally think about numbers. We think, for example, weather data would have temperatures, highs and lows of temperatures, rainfall, and these are measured in numbers. We'll have a date and time as well for that particular instance. How was the weather during a particular day? So that's again numbers. If you're also, for that matter, if you're looking at economy of a country, you would look at their production data, their consumption data, their trade of goods, imports, exports, volumes, population, currency exchange rates, all these kind of things. But they mostly constitute numbers. Um, but what we tend to do is we tend to dismiss a wealth of real world information that is being documented in the form of texts in a day-to-day basis, basically social media, news websites, journals, publishings, all these things. We tend to sort of not think of them as data, but they're like volumes of data, and historical data, for that matter. And they're just not in tabular format. And this processing of this huge wealth of information in the form of natural languages, everything that we speak, we think, our expressions using gestures, our whatever is being written in the news and social media, in journals, all these things, processing all these things is under the hood of natural language processing. um, and in short, NLP. And NLP also involves linguistics and behavioral studies, apart from computer science, AI, mathematics, and statistics. So that's a brief introduction. And then, so what is the big buzz of natural language processing? Why is it so different? Because um, texts are different from numbers naturally, and machine learning is basically statistical models under the hood. So we cannot process text as it is. We need to transform them into numbers. And we'll see precisely how to do it. If you see on this example here, the picture that I have here, it's a count vectorizer. So it basically gets the number of times a particular word has been used in a sentence. And if a particular word was not used in a sentence, it will be encoded as 0. So you can see that there's a good thing about this is it gets the counts of the number of words that has been used. A bad thing is it has loads of zeros, so there's loads of redundant information being passed there. So processing natural language is not a very easy thing. It might appear better when you're processing lexical English, so the words that you have in dictionary. When it goes into processing social media text, it becomes a bit more difficult, because then the spellings, the usage of emoticons, the usage of punctuations, they're not very static. So a lot of times regex do not work very well. um, and also the other techniques, so you need to be more precise in them, but it's very essential that at the end of the day, because machine learning is all about numbers, and the way predictions and forecasts work is basically advanced statistical models under the hood. You need to transform your text into numbers. And when you convert the text into numbers, how does this work actually? Um, you have a vector space model. What we do is, so in machine learning, we have feature vectors. So vectors are nothing but is an object that has both magnitude and direction. They're represented by some number that is that gives a definition of magnitude and direction, positive or negative. A feature vector is an n-dimensional vector of numerical features. So the number of dimensions is equal to the number of features, and these features are what we extract from these numbers. Uh, and how, what are these features that I'm talking about? So features are basically attributes that are used to address a forecasting problem. So for example, if you want to forecast forecast weather, you want to use uh, data as in what was the temperature, um, what was the highest temperature in a day, what was the lowest temperature in a day, what was the rainfall amount in that particular day, um, how much sun, what was the sun rise time, what was the sunset time of that day. So when you want to predict all these things for a particular day, you need instances of historical records of different dates, and for each date um, that would basically say that's one feature vector that contains a record of one particular day. And then many such feature vectors are going to constitute the entire data set that you're going to be using for forecasting. Um, and in text as well, in a similar way, whatever information you extract from these different from the natural languages, you will represent them as vectors in a vector space. And we will be using some similarity measures in order to assess how closely spaced these vectors are in that particular space. um, in the image here, you can see there are this is a typical two-dimensional vector space model, or just a vector space. Um, um, and that's the easiest for us as humans to comprehend. We've been, if you're from maths background, if you have studied coordinate maths, you would know that this we've been dealing with x's and y's for a long time. These are examples of how vectors could be plotted on a two-dimensional frame. Um, the first vectors, so there are two vectors. They're very closely spaced to each other. They're they are the angle between them is really small. So when you look at their cosine measure of that angle, it's almost near to 1. So that says that these two vectors have similar nature. The second one here, that's the angle is almost about 90 degrees. So it's neither similar nor dissimilar. So they're really like unrelated sort of a spacing or angle between them. And the last part here, the last diagram here, it has completely opposite directions. And so the cosine of that angle is almost -1. And the angle basically tends to be about 180 degrees. So that says that these couple of vectors are opposite in nature. And this concept is something that we've been using in natural language processing a lot. And then when you represent texts as vectors in the vector space, it allows us to use Euclidean distance or cosine similarity in order to find how similar or dissimilar are these different terms in a vector space. So in a text representation model, a particular vector is basically depends on the number of features you select. So it could be the entire vocabulary. So as huge is the vocabulary, that huge would be your vector space model. And then with word embeddings, if you choose a particular size of that word embedding of the vector space, you would have that kind of dimension for that vector space model. And then you will be using these metrics to assess how closely or sparsely are these located. And then one disclaimer here is that the distances in vector doesn't mean that there's semantic distance. So semantic distance means that it doesn't mean that if two vectors are close to each other, for example, the word happy and shopping, You might find them occurring together, but it's just that that model might have found multiple text that says that has happy and shopping together, but they don't necessarily mean the same. But it's just that they have been used in in similar contexts. So there's a difference. They're contextual, but they're not the same. Um, and then let's move into looking at briefly into how text representation models were. Um, this first example here, you can see we have a sentence, the mouse was chasing a cat. And we talk about vocabulary as essentially the distinct words that we have in a corpus or in text data. So corpus means text data. And so in the vocabulary, we have the, was, mouse, chase, and cat. And these are 5 different words that are present, distinct words that are present in that particular sentence. And we pick out mouse, cat, and chase, 3 different words, and want to represent it as a vector of that vocabulary here. So for mouse, you can see I've put a 1, and I've the, was, chase, and cat 0, 0, 0, 0. So this is essentially saying that this particular sentence or this particular word is at the 3rd position of that vector. Similarly for the cat, it's at the last position of that vocab vector, and then chase is at the 4th position of that vocab vector. And this is how we've been representing models. Sometimes if it was a multiple, if I had multiple sentences that had mouse, so maybe mouse was appearing like 3 times in it, so mouse would that vector would look like 0, 0, 3, 0, 0. So that would be an example of count vector. And what you see on screen is an example of one-hot encoding. So there are different other examples of text representation models. There are TF-IDF, there's Bagel Words model, there's Ngrams model. And the caveat of these are, so whenever you have these when you're using traditional text representation models, there would be huge vocabulary because you're filtering out not much. You lose contextual information because the mouse was chasing the cat. Um, that's that's not a regular sentence, so it doesn't understand the meaning of the cat was chasing the mouse, or it could be like the mouse was chasing the house, and the model will not make out a difference between these 2 sentences. And then evidently it'll have large corpus, it'll have a large vocabulary, and as much as you have vocabulary, there will be sparsity. So sparsity would mean there is loads of zeros in this data set. And because there's loads of zeros, that means redundant or zero information is being passed about the data. So that kind of also doesn't help in saving your computing power. It is going to cost you in memory and computing power requirements, and whereas you won't be processing enough information. So what is the way out here? So word embeddings in neural networks, it's a technique that kind of preserves the semantic information or contextual information. Um, it's a large corpus will have a large vocabulary, but we can reduce it down to a dense vector, not a sparse vector. So dense vectors will contain very less number of zeros or no zeros at all, and will be represented by floating point values. And it'll be of definite size, and that could be really much lower dimensional than sparse vectors would be. And therefore, that will also help us in memory requirements and computing power for word embeddings. So I've already introduced a bit about word embedding so far, and the theory behind it would be distributional hypothesis. So there's a famous saying in the word embedding world that says a word is characterized by the company it keeps. And it said that words have distributional representation. That means that the meaning of the word is distributed across different dimensions. And the embeddings, they preserve that information that are embedded in the context of the word. So see here, these are two sentences. I am at PyCon Sri Lanka and I am at my home. I would, so if you look at the traditional models, these two lines will not be very different for them. But when you're using word embeddings, so uh, the model is going to detect that PyCon Sri Lanka and PyLadies meetup have been used over a similar context, whereas home and room has been used in a similar context, because it'll see many documents coming up which would have PyCon Sri Lanka being associated with conference, Python programming, maybe networking, and and same for PyLadies. So it'll understand that PyCon Sri Lanka and PyLadies meetup belong to the same context, whereas home and room would be like would occur with words like house, bed, attributes of a home, say kitchen, or maybe an address. So uh, for word embeddings, it's easy for us and the neural models and wherever you feed the data to understand how closely these are spaced or how similar two terms are based on the context they have been represented in the entire corpus, how many times they have been these words have been occurring together. And then so word-to-vec model is a way of a school of algorithms. Basically, it's a family of model architectures that has been used for generating word embeddings, and it is usually done by initializing random vectors. For generating word embeddings, you specify what would be the dimension of that vector, and you basically optimize using stochastic gradient descent algorithm and learn from the errors. That's the usual part of machine learning. And word-to-vec model can be of two types, so continuous bag of words and skip cram. Continuous bag of words and skip cram, they do not um, vary vehemently by the actions, but they differ by the objective that you're trying to solve here. So so the first one here, continuous bag of words, it basically predicts the middle word or the actual word based on the 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 words that occur before that particular word and the couple of words that occur after that particular word. So your input is not the blank space, the words before the blank space and the words after the word space, the blank space, depending on the window size you've chosen. So this is for window size 2. So 2 words before and 2 words after is what you're feeding inside into the neural network, and you're trying to predict that one word. And then in skip-gram model, you're basically supplying the word, the actual blank space word, and then you're trying to predict what words are within a certain range. So that certain range is the window. So if it's 2, so it would like to predict the words that would precede it and the words that would succeed it. So essentially that word is there and the blank space, 2 blank spaces before and 2 blank spaces after it, and that's the objective of a skip-cram model. So that's how the objectives differ and that's how they work. And then somehow skip-cram has better results than continuous bag of words, though it takes a bit more time to train, and we will look at both in our use case. So how are these word embeddings used? These word embeddings are mostly used in deep learning, and Keras gives us embedding layer. that directly lets us use these word embeddings for to train a neural network for your problem statement. And then transfer learning is a buzz nowadays. So transfer learning is about using what you already have and adapting it for your data set. So Google from Glovey is from Stanford. So Glovey is another type of word and embedding. So it's not basically word to vec. So it's another school of another way of predicting the word embeddings. It uses co-occurrence matrices, and it was developed by Stanford. And then there's fast text. So there are three different well-known word embeddings data set that you can already use. So these are trained models. It gives out word embeddings and you can directly plug them in for your data set. And so this is also a type of transfer learning because you are using the data that has already been trained in thousands and millions of documents, and then you're basically using these for your purpose. Um, and then you can visualize and identify patterns in the corpus by using word embeddings. So it's time for some demo using GenSim. I'll stop sharing my screen and load the notebook. So I hope you have your Jupyter notebooks on with you. So we will look just basics of very basic EDA for this particular data set. It was already clean, so you would just need to probably do a bit of tokenization over there. That's it. Look at the data set a little bit, and then we will generate word embedding for that data. Um, and we will go into multi-class classifier only if time permits. Otherwise, the code would be available on GitHub, so you can imitate the code and look up for yourself. Um, so so here I've imported all the required packages, Python packages. You can follow along with using Google Colab. So I have, in cell number 4, I basically have imported data. And you can see that I have this data contains texts in one column, and in the second column it contains emotions, and there are basically 6 kinds of emotions that are in this data set and the corresponding text. So there's sadness, anger, love, there's joy, and um, there's joy, there's surprise, there's fear. So there's 6 types of emotions in this data set, and it has a training data, it has a test data, and essentially the test data and the validation data, they're same. So we will just look at training and test data. So we have 16,000 training data points and 2,000 test data points. And there are no null values in this data set at all. So here I basically use Plotly in order to have the number of what's the distribution of emotion tags um, to uh, to see what is the distribution here. So it's pretty much an unbalanced data set, and sadness versus joy sort of a problem, and anger, love, surprise, fear, they're really lower than 50% of the other datas. But I haven't handled this unbalancedness of this data set here for this particular talk. Um, so this over here, I'm basically setting the order so that every time I plot this for train test, the order of the data remains the same and the color coding remains the same. So it follows a similar distribution in terms of the test data again. Um, so for the data, uh, since it contains like 6 classes, this is a multi-class prediction problem, and for that you need to have one hot encoded vectors for your labels, and that's what I've done here. So I've used pandas cat codes to get the numbers here. It's not that necessary. You can well, it is necessary if you're using Keras. It's not necessary if you're using pandas. So there are different ways of coding. So I've been using. I thought that I'm going to stick to Keras for this one, and I learned a few things on the way. And then so you need to have these numbers as you need to have them as numbers in order to be able to one hot encode using Keras. So that's what I've done here. So I have taken train data. So basically the data sets text column, put them into train features, and train labels is a one hot encoded version of all the 6 emotions that you can see here. And then now we go into generating word embeddings. What does that um, word to vec expect? So I have used a tokenized word tokenized sort of data into the word to vec model. You can also use generator functions in for training the model, so that you don't have to have like the entire data set in the memory. And because I did not have as much data here, and just to keep it simple for everyone to understand, I've used for loops here. I have not used generators here. So this is basically tokenized version of into sequences of words. So basically the format it takes is you have sentence 1 and sentence 2 and all the words inside it into a tokenized version of it. That's all that I've done here. And then because I will go on into training a neural network, I wanted to see what is the length of these sentences by the number of words, because if you want to pass a data set into a classifier, into a neural nets classifier, you need to have all these sentences of one particular length, and what is the best length could be judged by looking at the distribution of of all the sentences that are in the corpus. So that's exactly what I've done here. I've taken the length of each of these tokenized texts, so basically taking the word count in a sentence and then plotted it. So it appears that if I use 20, that would suffice. 20 to 25 would suffice for me to standardize the length of the sentences or the number of words for each sentence to be used for training the neural network. And then I've used the vector size as 300. So you can use different vector size and you can test and train and see how different vector sizes work for you. I've used 300 here. And I've passed in the train and test features both in order to train it. And I will say, I'll tell you why. Um, when we go into when we go to towards the end of this session. So this length here, length of W2 of the model object, and is 16182. So that's the entire vocabulary. So that's the number of words this particular model has extracted from the corpus. So what you can do is, as a future work, you can train the model as tokenized train features, and then train the model on tokenized test features and see what is the difference in the vocabulary size. So that would be precisely a problem of using GenSim vectors in collaboration with Keras because you have to handle missing data values. So if you don't have a vocabulary in the test features that you have, if you don't have a vocabulary in the training features of the Gensing model, but you see that word in test features, you're going to run into problems. So that will be handled by embeddings that you have to either custom handle, or you will have to look for other embedding methods. Um, or and then once you've trained this model, you can look at the similarity scores of these different elements. So um, we had an emotion for sad. So lonely, confused, unhappy, angry, horribly, shit, cause, upset, these kind of words has appeared most frequently when the word sad was used in the data set. So they basically have been used in a similar context. Similarly, happy, if you look up happy and you get the top 10 most similar words to happy, you find contented. I don't know why. I think this is kind of noise, space, birthday, excited, report. So this kind of has a mixed sort of vocabulary, maybe because when people are happy, they write about different stuff. They don't just stick to saying that I'm happy. And then you can also pass a list of vectors, and it can give you the most similar words to that, the combined vector as well. So that shit, damn, horribly, so they're not good words here. And then you can also, add, so you can do regular vector operations. So you can, so this is basically just adding, and then you can use negative, so minus the lonely vector. So what you have there, that's kind of a mixed response here. But you can test these things uh, in uh, when you run the notebook. And then so basically after this, you can also use PCA. So this is a horrible diagram. But that's only because the corpus over here that I've used has got much larger vocabulary. So that's why we've got this horrible plot over here. But you can use PCA. So right now our vector has 300 dimension. So this would be like how the word happy would get represented. It's into 300 300 dimensional vector of just to represent the word happy. And that the 300 dimension has been reduced to 2 dimensions to fit here. So I've used PCA algorithm in order to get this. So that's why when you project that huge vocabulary into a 2-dimensional space from 300 dimensional vector space, it is bound to look like this. But what you can do is you can download this, and you have so there's an embedding projector from Google, and you can use this model to visualize certain things, how these words are spaced in a in that particular in a vector space model. You can click on a particular word and see what are the related words there in that vector space, and it's not definitely 2-dimensional. So yeah, just here, so you can use get vector in order to get what is the vectors, what are the vectors here, vector data here, and you can see the shape is 300. And then so after this, all I've done is um, so once I have got this model, I've converted all the entire corpus into into the sequences of the vocabulary that I have here, and basically I've used them to create a multi-class classifier. So over here, remember how I used 20 to standardize the length of words. So I basically used pad sequences from Keras in order to standardize the length of sentences and into 20. So you can see how, we have x is equal to 20 here. That is basically standardized for all sentences. The count is 20. 20 words are there in each sentence. And then here I've used the embedding layer where I have the input dimension as the vocabulary size, which is about in the order of 16,000s. The output dimension as the vector size. You have to give the weight. So embedding matrix contains the entire vector space of the vocabulary versus the vector size. And then you've got the input length. So that is the length of the words, the length of the sentences by words that I'm going to provide to the model. And then I've used dropout and LSTM and dense vectors, layer at the end to facilitate to the multi-class classification. And because I'll be predicting 6 different kinds of classes, I've used 6 here at the last dense layer, and I've used softmax activation point. And then basically I've trained the model. The optimum epoch would be 3 epochs that I would rather use between 3 to 4. And so this is how the precision and the precision recall F1 score, basically the report that I have here. The accuracy have increased over the epochs, and it's almost 90%, 82% here. So that worked well. I think, yeah, that's all from my side today. Do you have, I hope you enjoyed this talk. Do you have any questions? So I can take a few questions if you don't mind.
All right, so we have a question. Is it still supervised or is it unsupervised if I'm using word embeddings for a spam filtering project that I'm working on? I've got a data set of positive and negative content.
So you're using word embeddings for spam filtering projects. So your work is still supervised.
Yes.
Your sort of positive and negative contact. Yeah, your because your tasks, so basically supervised or unsupervised would be your task that you're looking at. So because your data set is pretty much labeled, it has positive and it has negative content. So your work is still a supervised work. There's a Q&A section.
Does grammatically correct sentences provide more accuracy to the data set they are by the model?
I don't think so. But then I think usage of correct spellings would be better. I think if even if the sentences are grammatically incorrect, I think the model is going to perform okay.
All right, I think we can move on to 2 more questions.
Yeah.
What is better, Python or Keras API?
So Keras is basically for using Python. So Keras is a Python package versus Python is a programming language. So you can use Keras, or maybe you could have asked Pandas or Keras, which one is scikit-learn or Keras. But Python is a programming language, and Keras API, it's a package in it that is provided by TensorFlow for you to train neural networks. So these two are very different concepts. Um, Not sure what to answer there. Sorry, lost your voice there. So word embeddings, they give you the context rather. That's how it improves the textual representation. So when you got it also reduces the dimension size so that you it makes the representation lower dimensional, and and then neural networks see how closely or sparsely these vectors are present. So it basically improves the efficiency of the entire classification or clustering model, whatever you're looking at. And the example of how you can use embeddings for text classification features is already there in the notebook. So you can just refer to the notebook and follow through the code, and you should be able to work on them. And you have my contacts as well in the PowerPoint. So if you want to contact me for anything, any other questions, I'll be happy to answer them over LinkedIn.
I think we can wrap up the Q&A round now. Thank you to everyone for your active participation. Thank you, Ms. Roy, for making this session a great success with your knowledge. And a
Thank
small
you so much,
reminder,
Hashini.
thank you so much. And a small reminder that you can join the booths of Matific Sri Lanka and ISEC to have discussions with them and enjoy the interactive sessions by standing a chance to win the exclusive gifts at the booth. Also, another kind reminder to reserve your delegate pack with the t-shirt to showcase yourself with pride as a member of the Python community. The links for reservations are posted in your delegate group, so please make sure to reserve the pack as soon as possible because the stocks are limited. Next, you can join our session 5, Data Lifecycle with Python by Mr. Sahan Bulatwela. So hope to see you in the next session. Thank you.